So thank you very much. I clearly thank the organizers. But it's often like this. If you don't expect much, you can only be positively surprised. And this was really what happened to me this week. I learned a lot. I saw many new connections to people where I did not know that. So particular Chris from Poland, Hiba from Denmark, Bruno from Italy, clearly Oleg, Ukraine, now Germany. Okay, so my talk will be, I announced a different one, something with random sampling and optimal sampling, and it's the same talk, just a different first slide, because I really wanted to emphasize the word complexity already here. It's kind of my research area is information-based complexity. I will give you a very brief introduction into it. But if you are already familiar with some concept of complexity theory, typical P equals NP things, right? Then you hopefully know and will excuse me for the fact that some of our assumptions are clearly unrealistic. But that's science, right? You make some assumptions, you prove some results, and so on and so forth. And yes, that's very theoretical, but I think to myself, if you work with numerical algorithms, what is often missing are benchmarks, theoretical benchmarks, complexity results. So you present a result, you have some error bounds or whatever, you need to compare it to something, right? And there is stuff that is done to compare things if you work with multiplication of two matrices, or if you work with some other discrete problems. That's well accepted that you need to study complexity theory. It's well accepted that if you present a polynomial time algorithm, your problem is most likely not NP, right? Not NP hard, and so on. That's just well known. It's not so well known in numerical analysis. It's not so well known in machine learning in general. I'm one of the ambassadors of this field to change that in the future. I think it's just one perspective. My perspective is different to basically all perspectives I have seen this week, because I'm not algorithm oriented in the first place. Of course, algorithms will play a role. It's about numerics, it's about approximation. I'm problem oriented, okay? I fix my problem as I would like to solve it on a computer, and I'm working somewhat under the assumption that I know the optimal algorithm, okay? I'm a mathematician, I can do that. I know what an infimum is, so I can do that. So let me explain that in a little bit more detail just to get my perspective on, say, machine learning in general. Okay, so in general, what we want to do is we want to compute whatever this precisely means, an approximation of a function f in some class capital F, based on a preferably small number of information. I will explain everything that is in quotation marks. I will explain a little bit more better, a little bit more detailed. So we want to have a small number of information because there are many reasons for that. My most favorite reasons are, first of all, we don't know F. We have a physical system. We want to study weather. We want to study whatever, a piece of hot metal. And we just don't know it. We just don't know what's going on inside. We just don't know how the weather goes forward. We only can take some measurements, and a measurement might be costly. The second one, which is, I would just say, even more important, and but it's different in flavor, is you have complete knowledge of your object. You just have it. You have it on your computer, or you have it on your sheet of paper, or whatever you have, but still you need to compress it because you want to work with it on a computer, right? Objects can be infinitely complicated. They might be easy to study for a human, but still a computer can only work with a finite number of informations. It can only work with it has memory problems and so on and so forth, right? So you might want to compress it because of computing issues, also a thing. In both cases, you basically want to represent your infinitely complicated object but just by the finite number of numbers. And the question is, how many numbers do you need? Okay. And of course, not only this, what information are you allowed to compute of your object? And how important is this choice? That's the general theme of the field of research I'm in. And if you are afraid of this F element F thing, I will come to that in the next slide again, but it can just be seen as the a priori knowledge of your object. It has some derivatives. It is a function on a domain, and so on and so forth. Right? Okay. So the general framework of information-based complexity, maybe I go to this side, I don't know, is always the following. You have a set of inputs, that was the capital F on the last slide, which basically means what do we want to approximate. You have another normed space G. I will only take G equal to LP or L2 spaces. comes on the next slide. So this norm space G is just how do we measure the error? We want to measure it in a mean square sense or in a uniform sense, or maybe some even more crazy stuff. Okay. And the third thing that kind of separates our group from the classical approximation theory is that we are not looking for the best unrealistic approximation that you can get, that only God can get, kind of. What we want is we want to come closer to numerical algorithms, which means we have to fix what kind of information we are allowed to collect. Okay, we all did that most of us did that during this week, and I will come to examples in a second. I will really give you a basic example as I would give to my bachelor students. I hope that you will understand all these things then. Okay, so what is our data is the last question. And the goal is we want to learn or approximate, use whatever word you want, F element F, using only information from this class. The last one is double, or whatever. Okay, so let me now say what everything is, right? And information in general is in our concept just the most general thing you can imagine. You have a function C, or later they will call it differently, but whatever, some function, call it C now, real-valued function out of your class, and this is called a measurement. And an information of your input is just a measurement applied to the function itself, okay? So C of F is just a number, and so on. So this is one measurement, C, give you one information called C of F. And in general, of course, we have no access to arbitrary measurements. Either you are a physicist and you can only measure some frequencies, or we are machine learners and only have function values, or you make medicine and you only have values of an X-ray transform or of a radon transform, and so on and so forth, right? So you have to fix that in advance because that's just your problem, right? So you have so the admissible information, which I call lambda, just for the next slides, I will stick to function values completely for the rest of my talk for the sake of complete simplicity. Typical informations are, as said, Fourier coefficients, radon transform, so expectations of a function f, like values of a radon transform, values of an X-ray transform, whatever, derivative values. But just to keep things simple, I will only talk about function values here. Okay, so now the thing is, every information I can collect is just an evaluation of the function at a point. So C, these guys C, are just the Dirac functionals, to say it in mathematical terms. Here's something cut off, probably I read it. So again, there are 10 different settings. If you know complexity theory, there is not only P and NP, there is P sharp and sharp NP, R, P, S, L, whatever. They are increasingly complex. And of course, there is the same in our field, right? So there are many different choices what you allow as an algorithm. So the setting I will talk for the half of the time here is I'm free to choose the best measurements. Okay, I'm free to choose the best measurements in advance. It's half of the talk. Then the rest of the talk, or at least a part of the talk, will be these measurements are random. But of course, there is the same important problem is sometimes measurements are fixed just by your application. This is again a different problem, typically called optimal recovery, is somewhat not really, we have intersections, but it's a little bit different, but different settings. Okay. Now I have my measurements, but I want to solve my approximation problem, right? So I have my measurements, and then an algorithm is just defined as an arbitrary mapping, could be nonlinear, linear, whatever, just some function, which maps my n measurements to some element of G. Remember, G is just L2 or so. It's just the output of this function phi is a function, and this I call an of f. In machine learning literature, you would probably call this f hat or so, right? So that's your estimator. We call the estimator an of f for different reasons. First, a is for algorithm, n is for the number of measurements. And we want to have this an and not just f hat because I consider an as a mapping, right? And if I consider it as a mapping, I clearly need to distinguish between its input and its output. And we all know how to do it. We invent a notation for it. So that's just the output of my algorithm. That's my estimator. That's all I need. So I consider the minimal worst case error here. Let me say that's one setting. Again, there are millions of them. I take that because it's hopefully easier to understand. If I would take an average case or whatever, I need to introduce some more measures, some more parameters, some more whatever. I just want to stick with the least number of parameters possible, so to get you a little bit introduced in our subject. So the minimal worst case error is now specified, as I told you. I only need F, I only need G, and I need the number of admissible information. What is this quantity? I consider the error of my algorithm AN, which is the difference between F and ANF. I measure the difference in my normed space G. I then take the supremum over all F. So this here, inner, is the worst case error for one specific algorithm. And then I'm just taking the infimum over all algorithms. Okay? I'm a mathematician. I'm not afraid of infima. So everything that looks like this can now is an algorithm for me. I can just take the infimum of the class and get this. So this object here is just the best you can do. If you only allow function values, if your class is F, if G is your error measure, then this is, as the word says, the minimal achievable worst case error of anything that you can call an algorithm, if you accept this as our algorithm concept. Okay.
One question. So both A and F has to be in the same space, right?
Yeah, of course, because otherwise the norm makes no sense. But clearly F is usually, say, very smooth, and G is just L2.
But if you say normal G, so it means sort of like smaller space, right? F smaller space than F.
Exactly, yes. F is, say, a function of a class of smooth functions, and G is just L2. So of course, the class F is much smaller than the class G. And by the way, to get that this one even goes to 0, you need something like F is compactly embedded into G or so. So you really need a small class otherwise, but that's obvious. Yeah?
So when you talk about L2, the function evaluation is not really well defined.
But it is defined on F.
But you could change F at the evaluation points and...
No, big F is a Sobolev space. Is function values are defined, right? And then I measure my error on L2. What is the problem?
Okay, I understand. So the space you pick F from is smoother than L2.
Yeah, yes, of course. Function values must be defined to talk about function values. And I will usually assume it to be a Sobolev space for the sake of this talk now. Or Lipschitz function, yeah?
Oh, F could be very large, like L2 function. But your capital F is the polynomial.
No, capital F is not just polynomials. Capital F is an infinite dimensional normed space.
Example, you said this F is larger, F is smaller.
Sorry, yeah, capital F is the smaller space. Capital F is must be in G. But that's only slide 3, so maybe you wait for examples to forget things. Okay, so let me do things a little bit more specific, just for you to. So this was the general concept. If I want to. Questions, please, to me if you want. Of course, yes. I'm just doing recovery. You could do solutions of differential equations. You could do a computation of integrals. You could have much more complicated problems. I just want to keep it simple for you to get into. Okay, so this is, as I said, the general thing. For all inputs in F, with error measured in G, with information given in lambda, this is the best you can do. Too many parameters. So let's go over to what I really want to say and what's my favorite kind of subject, that's so-called sampling numbers. So that's what I just wrote here is the same as I wrote here when the information is fixed to be function evaluations. And the recovery mappings are even linear. Okay, let's explain it again. So this quantity here, Gn of F with LP, means if I want to approximate a function F by a linear method, this is just, think on interpolation, Lagrange interpolation, for example, right, is of this form. So you are only allowed to compute function values. You are allowed to combine these function values in a linear way as you wish. This is only one algorithm here. Then you take the worst case over all functions in the class F, say, again, unit ball of a Sobolev space or so. And since you want to know the best possible algorithm of this form, you just take the infimum over all sampling points and all LP functions for the reconstruction, okay? So this quantity here is, again, the best you can do with a linear method that is only allowed to compute function values. I think many of your talks, at least, have been exactly in this setting, right? So a lower bound on this quantity gives a lower bound on your spline method, so to say, to be a little bit provocative. I know that one has to talk about details there, but on linear algorithms and function values, yeah. And the idea behind that is, this is the most easy thing we can imagine, right? If you want to do approximation, everyone knows about linear methods that only use function values, interpolation, least squares, whatever. They are all linear, they all use only function values, they are all of this form. Okay. Yeah, proving something on this quantity, yeah, go. From Vietnam. We come to examples in a second, please. I talk about this later, please. I will come to examples. I repeated it 3 times now. Probably I'm too stupid to say it, but there will be examples. Okay, so this is clearly the class of linear algorithms using function values. And proving something on this is worthless, right? It's just a number. Every G and F is just a number. You need to compare it to something. And that's complexity theory, right? The question is to compare it to what? And again, millions of options. I give you the most well-known one, and they are the so-called Kolmogorov width. The Kolmogorov width is the error of best linear approximation, right? So you have your function f as here, but instead of taking the output of some algorithm, you just take the best approximation on a fixed space Vn. Again, you take the worst case, and at the end, you take the infimum over all possible subspaces, right? In your case, the n-dimensional space could be splines, tensor product splines up to a given order, or just polynomials, or frequent or trigonometric polynomials up to an order, whatever, right? You could just fix one, but this quantity here even takes the best possible n-dimensional subspace and then the best approximation on it. For us, that's a natural benchmark, right? Because if I prove that a sampling algorithm, maybe even an easy sampling algorithm, can get the same error like the Kolmogorov numbers, then we know that's done. It's an optimal result. There cannot be a better result because I only consider linear methods, right? So proving that these two quantities are of the same order or even of the same size up to a constant is a very powerful result, okay? It just shows you that we already understood the problem so well that we can design sampling algorithms that can catch up with the best approximation on a linear subspace, okay? It's a quite powerful result, I can tell you. It depends on the generality, of course, but this quantity, the Kolmogorov width, are often used in the literature, and you have to be aware that there is no relation to algorithms at all. No one tells you that if the best approximation on a linear subspace is a small number, decays exponentially or whatever, no one tells you that you can achieve that by function values. No one tells you that you can achieve it by any algorithm, right? That's just a different quantity. This is the quantity. If you say that you can reach best linear approximation with a sampling method, if you're claiming this, you claim that Gn and Dn are the same. And you should be careful with statements like this. That's the point I want to make. Okay, I want to make it a bit simpler parts in the talk. So whenever I leave out the LP here, I only mean L2. So the easy problem of approximation in an L2 sense mean square norm. If I haven't said that, whenever I say L2 or whatever, the domain and the measure are completely arbitrary. I don't need any assumptions. Throughout my talk, nothing, okay? Your domain D can be a subset of RD, can be just the line, but it can also be an infinite dimensional stuff. So you can have everything. I don't need any assumption during my talk on the domain of my functions. Okay. So how good are function values? I already told it to you, right? So the DNs, the Kolmogorov widths, for many problems of interest, they are very well studied. For 100, not only, say 80 years, Kolmogorov is not so old, but whatever, but these numbers are studied forever. They are known for a lot of classes. The GNs are very hard to analyze, as you have already seen during this conference too, right? We are still discussing what is the best you can do and this and that. So the GNs are kind of case specific from time to time. So they are harder to analyze. But we clearly have first that the sampling numbers are always larger than the Kolmogorov numbers. That's what I explained to you already, right? And now the question is, how large is the difference between these two? And if you want to answer this question, the thing is, you need assumptions, like for every theorem. So what properties of F are essential for such a comparison? Again, Dn is best approximation, Gn is approximation based on samples. Okay, let's come to examples to get a little bit better feeling to it. And this is copied, I will show you the paper later. So this is the easiest example you can do with it. My class F, which I call F lib for a second, is just a class of Lipschitz functions on the interval. Okay, you have functions on 0, 1, which satisfy a one Lipschitz condition. This could be my class F. Okay. For every given set of points, this example is very instructive and very interesting from a complexity point of view, because everything can be done explicit. You don't need an infimum. You can really write down every object that I told you on the last slides. You can really write down a formula for it. Okay, so given a point set where we want to compute our samples and the corresponding function values, all functions that are consistent with the data, right, can be described. Look here, these are the sampling points, the blue ones, right? And just by our Lipschitz condition, we know that every function that is consistent with the data and is in the class itself, is itself a one Lipschitz function, must be somewhere between the blue and the yellow function here, right? So we know that. We know it. So if I now construct an algorithm for it, right, I have to put it somewhere in the middle. And even, you might already see, there is an optimal choice to do so. And this optimal reconstruction is often called the Chebyshev center of a set. If you fix some data, or it's a codimensional subset, a finite codimensional subset of your whole set, then there is a Chebyshev center of it, which basically means it minimizes the error. It's a well-known concept, more in the Russian school, but it's well-known. And this is the yellow line here, okay? So if I have my data, then at every point, I'm just putting the approximation really in the middle of the upper and the lower bound, because this minimizes the worst case error. Okay? But this algorithm is complicated. You already see that's complicated here. You could do easier stuff. You could do something like using the linear spline. I mean something different with spline than some of you do. Please don't throw stones at me for that. I can describe it a little bit better what I understand when I hear spline, but that's something for the very end. Okay, so this is this dotted line here in the middle, right? That's not an optimal algorithm, but it's easy to prove that it's close to optimal. It's optimal up to a factor of 2, so it's fine. It's also a good algorithm for this one-dimensional setting here. What is the cool thing about working with optimal algorithms? If I assume for every problem I know the optimal algorithm, the whole question becomes independent of algorithms. I already did the infimum, right? So it's like taking the infimum of a function is no longer a function. It's similar here, right? It's just a number. So in this case, it means if I'm working with the optimal algorithm, I might hope to get a formula that is interesting in its own right. And for this specific example, that's really the case. For many other examples too, it is the worst case error of the optimal algorithm based on the function values x1 up to xn, they are fixed, right? Is just the LP norm of the distance function. Which means if you now making geometry, and in principle you don't care about algorithms, but for a reason you study some averages of distance functions, then to some extent you are studying optimal algorithms for numerical approximation. Okay? So which means the stuff I'm doing is quite close to geometry questions, has nothing to do with algorithms, but we can interpret them at the end as questions about algorithms. But this is really for the specific example, kind of. Okay, yeah, maybe there is not so important. So maybe look at this picture here, right? You might already see with the picture that that if you want to have a small error, then you want these guys here to be small, right? As small as possible. And I hope you believe me that they are the smallest if you make the distance between them equidistant, if they have the same distance. It's well known, right? So equidistant points are optimal. I will come to the references in a second. So this means the sampling numbers and the Kolmogorov numbers in LP of Lipschitz functions are of the order 1 over n. These constants are partly well known. There's the forward constant and stuff. So it's really, people even studied the explicit constants, they are known. Okay, that is for this specific example, sampling is as good as approximation from the best n-dimensional subspace. Some comments. First of all, there are many optimal subspaces for the Kolmogorov numbers. That's not a unique question. They are, you could take polynomials, you can take splines. yeah, there's a lot of stuff. I really suggest to look at the references, some of them. And the same as we have for Lipschitz functions, the same statement basically is true for Sobolev spaces on the real line. So if you go away from Lipschitz and make a Sobolev class, will also work. Okay. Let's say something to the references here. So the Kolmogorov numbers and best approximation is really studied forever, right? Clearly starting with Kolmogorov in the 40s. Some of these results, although I just proved them to you on 2 slides, can be very hard if you go to L1 or L infinity approximation. That it's not clear what the best subspace is. There are still open problems if you go to higher dimensions. In this one-dimensional example, this was solved by Tikhonov in the 60s. And Pinkush in the 80s would have excellent surveys about this stuff. So there you can find, I think, for this particular problem, 7 different optimal subspaces in his book. It's easy to find. So that's one. And the second one is the sampling numbers. They haven't been studied that long because this notion of complexity was not there. The godfather of IBC, information-based complexity, abbreviation IBC, kind of the godfather was Bachwalow. He was kind of the first guy who really studied conceptually all these complexity questions for good, for fixed information, so to say. And for the precise result here, I am not sure if I'm quite sure it is somewhere in his paper already. The upper bound must be much older because it's about interpolation of a one-dimensional function that's old, right? And the other references here, so Sukharev extended that to higher dimensions, and CLA and Shoemaker are for us really the first kind of references if you go to Sobolev spaces or more general domains and so. So it's just these references here are some kind F for extensions and not precisely for this result. As a general comment, I think it's good to cite old papers. I only need one argument. I want to be cited in 100 years. So I must behave the same. And so I'm citing people that made research 100 years ago. And I think that's just fair if they invented that. Okay, one dimension, boring, right? Let's see. Let's go to higher dimensions and higher smoothness. One might think this classical smoothness assumptions here is a very well-studied object, and it is. The problem is it's not what you hope to see then. So that's a very common to use this classical smoothness assumptions. You just say you take functions on the cube as derivatives and take the norm bounded by 1, which means all derivatives, all partial derivatives up to some order, total order, are bounded by 1. It's known forever. The optimal order for them, for sampling and for Kolmogorov numbers, is n to the minus s over d. People know that. Sometimes that's called the cursive dimension, wrongly, but okay. So this is the thing. But this guy only tells you that the number of function evaluations you need is some constant divided by epsilon to the power d over s. If you want to get an error, epsilon. Okay, that's the only thing that tells you this. Is this big in d? Is this does this show you that you need a big number of function evaluations for large dimensions? No, why? You need to know CSD for that. If you don't have a lower bound for CSD, if CSD is 1 over log d, then this guy even goes to 0. It even gets easier if d goes to infinity. And it's easy to write down a lot of examples where this happens. The problem then is that if someone is working with a class like this and proves the result in higher dimensions, that's useless. It was just a wrong normalization of the whole problem, because already if the problem gets easier with higher dimensions, you did something wrong, right? But this question really depends on your chosen norm. So one has to be careful when you work in high dimensions that your problem is really well normalized. Let's put it like this. In this specific case, it was expected, but not proven for a while. It was proven in 2016 with Eike Hinrichs, Erich Nowak, Henryk Wozniakowski, and myself, that even if you consider nonlinear sampling algorithms and only L1 approximation, which is the easiest, right? So LP approximation with linear methods is clearly a bigger error, right? So even if you allow nonlinear methods, I did not define that, but I think it's obvious what it means. You get a lower bound, which has something like d times this. So it depends linearly on d, which means if you rephrase it, if you want to get an error epsilon for every function in your class, the number of function evaluations grows like d to the d over s, right? So you really need, for every fixed S, for every fixed smoothness, your function have 42 continuous derivatives, all are bounded by 1. It's an extremely small class, but still for this very, 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 very small class, you need d to the s, d to the d over 42 function evaluations that you're dead with if d is equal to 100 or so. Okay, so this is called the curse of dimensionality, and it basically shows you that other model classes are needed for high dimensional approximation. We should think about something clever, about something better. And luckily, half of you were working on this. I just see it from a different perspective than you do, but it's very much related, and I will explain that to you now. These classes are my favorite example. Basically, proving the optimal order of convergence for these classes is probably my biggest achievement in science, and probably will be. So let's see if I can give you a little bit of my enthusiasm about this result. So one interesting, my favorite example of this are Sobolev spaces of mixed smoothness. So what you are doing is you define normal Sobolev spaces. For simplicity, I do it on the torus, but they are all, you can do that also in other cases, right, with a little back measure. And this is the typical Sobolev norm, but we use as a norm what Ullrich called coordinate derivatives or coordinate degree. And I do kind of this coordinate derivatives, but we call it dominating mixed derivative. And in recent times, this because it's the highest order derivative is the dominating one. But I never really liked the name, so I skipped the dominating. So Sobolev spaces of mixed smoothness are defined like this. You just take the sum over all alpha that are either 0 or s in each direction to the d and take the corresponding partial derivatives, which means the highest order derivative is this one. I'm allowed to compute, say, if you take the space of smoothness 1, I'm allowed to take the first derivative in each direction, which means I can compute a derivative of total degree d, but only this one of total degree d. I'm not allowed to compute any other of total degree d. Okay. Yeah, the good thing for this is I wanted to go into details, but the clock shows me no. So let me just say, so these classes are tensor products of univariate Sobolev spaces. And tensor products are kind of easy to define, check Wikipedia. So, and if I have a problem in high dimensions, my first idea would to use tensor products. And I can tell you people in the old Russian school did the same. The main problem is they really fastly realized that those classes are extremely hard to study. They have some geometry where balls are replaced by hyperbolic crosses, and hyperbolic crosses are terrible to work with. So just take the hyperbolic cross, if you know what it means. So you have 1 over x, and then just flip it in all coordinate directions, and just try to compute or estimate the intersection of two hyperbolic crosses depending on their distance. It's only, you can do it as, you can, already a student can do it. I already tried it when I was a student. And you will see what kind of problems you are facing. It's just because the hyperbolic crosses are infinitely big. Their intersection is never empty, right? Makes it hard to work with, I can tell you. Okay, why are they important? I also like to motivate my stuff, right? So they are extremely important because they reflect some kind of symmetry of parameters in high dimensional models. Think, for example, of particle physics. You have two particles, and for simplicity, think these particles are on the real line, right? They can be specified by one parameter, right? If I now can compute a derivative for one particle, and I can compute the derivative for the other particle, it's obvious that I can do it for both, right? They are independent. So there must be kind of a model that respects that some parts of your parameter space have nothing to do with each other, which means if I compute the derivative in one variable, this should not forbid me to compute it in another. And in this sense, mixed smoothness is really the right model, not in this simplified case, but the thing here, if you look to the paper of Isar and Tant, the very famous numerical mathematician, he proved that the solution of the electronic Schrödinger equation is of a certain type of mixed smoothness. You can check that. And if I tell you that about 60% of every money on earth that's spent, every money, including everything that you can think of, is spent on the solution of the electronic Schrödinger equation, you might not believe me, but you can believe Wikipedia. So this equation is important to design new materials, to design new drugs, to design whatever, right? So that's an important thing. I have nothing to do with it. I just tell you these classes really appear in applications, in important applications. Yeah, they also correspond to concepts of uniform distribution theory. And for you important, I just added that. If you consider these classes here, and you think about a good re-spaces, we would have an orthonormal basis, would be good, right? But an orthonormal basis for a class like this will never be compactly supported. Will not have a small support. So, we don't need to work with orthonormal bases. We can work with re-spaces, which are close to orthonormal bases. So you can see the norm in your space at the coefficients. Then the tensor product B-splines are re-spaces for the space. So you can really compute the Sobolev norm if you work with tensor product B-splines, if you want to, if you do it the right way. And for me, the main and only reason I need, I'm a mathematician, tensor product of univariate Hilbert spaces sound so simple that I just want to understand them. And that we don't, in some settings, is a lack of knowledge, and we have to close this. And so it should be easy to understand. And I'm trying to advertise some of that. Okay, so what is known? Again, if you do that I now fix only to L2 approximation, because the other formulas get a little bit complicated. So the Kolmogorov numbers of this class in L2 are well known. Babenko and Mityagi in around the 60s proved the upper and lower bound. And they proved that you have n to the minus s, and then some logarithmic correction with a d there, right? So the main order of convergence is independent of the dimension, which actually gives you a hint that this could be a good model for high dimensional problems. Okay, that's known. Now sampling numbers. Smoljak, the famous Smoljak algorithm, you probably know it under the name sparse grids or tensor product grids, or there are several names for it, but we call it Smoljak's algorithm. It's just fair, he invented it. Proof that if you do it with function values, if you take the sampling numbers, you get almost the same, but you have some additional d minus 1 in here. So this plus 1 translates into a d minus 1. There was nothing going on for 25 years, although I can tell you many people tried. And then they removed the 1 and made a 1/2 out of it, right? It's just, yeah, it's an improvement, but this is already kind of famous. I'm not T. Ullrich, it's not me, it's Tino Ullrich. We are not related, we are only friends. So, yes. And by the way, this S larger 1/2 is necessary so that the functions are continuous. Otherwise, function values make no sense. Yeah. And it was the prevalent conjecture that this one is sharp. I have no time to explain you why this is the case, but it was considered as a sharp. And maybe, I'm not sure if you have a feeling on that. So let me just skip it. I will show to you that for these important classes, sampling numbers and Kolmogorov numbers are just of the same order. You don't lose anything, okay? And we know that from a general comparison. And the thing with general comparison is, it does not only hold for this class, it basically holds for some general classes F. I think I have to hurry up a bit. So there are some earlier results, blah, blah, blah. We don't need that. Let me just prove my theorem. So quite some active years, I have to admit. Since 2021, a lot of people were involved in that. So in any case, Mathieu Delbault, excellent French mathematician, young mathematician. David Krieg, my younger PhD brother. Myself, again, David Krieg, Katja Poczarska from Ukraine, again, me, Tino Ullrich, Abdullah Shkifa from Morocco, and again, Delbault, Krieg, and Ullrich. So there was quite some work done on this. And you see the theorem comes without any assumptions, basically. You have some class F, which is embedded into L2. The separability, forget about that. You need a metric space to say what you mean by continuity of point evaluations. You have functions on a class D, and yeah, you want that point evaluations are continuous linear functionals on F, then you just have this bound. So if your Kolmogorov numbers are suitably summable, you get an upper bound for the Gn. And to answer some of the questions we had already, there is no hidden constant here. You don't need hidden constant. In the beginning, we had constants like 10 to the 7, or there exists a constant or whatever, but we finally managed to really get it down to the precise result. That's easier to digest. It means whenever you have a class of functions where L2 approximation can be done in some order, say n to the minus alpha log to the beta, with arbitrary linear subspaces. You think of the subspace. You have a subspace, you assume it has a certain order, then clearly the n is even smaller because it's the optimal subspaces, right? If you assume that, then I tell you there is a linear sampling algorithm that can do it. There is no reason to think about complicated, adaptive, random, whatever methods. There is no reason to think about some regularization that it depends on data that you don't have, and so on and so forth. But let me repeat again, I'm only talking about information cost. In my world, an algorithm is, I don't think about computational cost here. Okay, and yeah, if this decay is larger than 1/2, they get that. If it's equal 1/2, you get some logarithmic correction, and otherwise it does not decay at all. And you always find some f such that these bounds are sharp. I'm skipping the end. That's probably more interesting here. So our goal was really not to prove good upper bounds. That's how science sometimes works. I'm a complexity theorist. I wanted to tell machine learning guys that I don't know what they are doing. And I wanted to tell them that there is at least one example they have in mind that they can work on, where their assumption that you have IID random data is just a bad one. I wanted to find one example where you get where the optimal result is good, but the IID result is very bad. Just to get some caution into the game, right? To advertise that. And unfortunately, so we somehow thought it's not so good. We somehow thought there must be an example. And to some extent, unfortunately, we were not able to prove the lower bound. And we were not able to prove this lower bound for years. And then we thought, let's try it the way around. Let's check if it works otherwise. And the proof was extremely simple. And so we basically wasted some years of time. But whatever, we proved an upper bound. And we proved that even a very simple algorithm gives you the optimal result if you do it the right way. And this is thanks to random matrix theory and geometry in Banach spaces, clearly. So what is the simple algorithm? It's just weighted least squares. Okay. You take weighted least squares, forget about the basis. Think the basis could be your B-spline basis. Assume Vn is always an n-dimensional space of your B-spline basis here, right? You just take weighted least squares like this. And yeah, one can argue about the weights. We have an explicit formula for the weights. We can really give the weights depending just on x. And the weights that you see here, this formula, it looks complicated. There are many versions of it by now, depending on the reproducing kernel of the space or so. But I just want to show you everything here is explicit. And it depends on your chosen basis functions. You choose the basis functions. If you can compute these sums, you can also specify the weights. And not only this, you might see what this could be here. This row guy is a probability density. Okay, so we not only have the weights, we also have a probability density. And now the magic comes kind of, if you sample your points with respect to this probability density, which might be a complicated one, it's hard to evaluate, it's hard to sample from, right? Whatever, I'm doing theory. If you sample from this, then there is a universal constant C. That was our first result in 21, me and David, such that the worst case error in an L2 sense can be bounded by this infinite sum with high probability. And we still needed a bit of oversampling, so to say, right? You remember our other result was there was the same n on both sides and so on and so forth, right? So there was some oversampling involved. It only holds with high probability. But okay, the rest is terribly technical, but it's only subsampling based on frame theory, basically, and graph sparsification. There's some big progress in graph sparsification over the last 20 years. Was a lot of help, I have to admit. Okay. Let's come to my favorite example. I told you it's a difficult thing, right? It's a difficult problem, it's difficult density, all these things, right? The funny part is, for this space, because I chose periodic functions, the optimal basis that you need to choose here is the trigonometric system. And the trigonometric system is in absolute value always 1. But if the absolute values of all basis functions are 1, this function here is just constant 1, right? Which means I can apply our theorem just with independently and uniformly distributed points. So this result shows you that if you take n points in the unit cube, just independent, uniformly distributed, and you make unweighted least squares with these points, then you get this error bound. In the worst case, not random. There's no randomness anymore. This result here, this worst case result, holds with high probability. So not that you need new points for every f. It's a worst case situation. Okay? And now the crazy stuff was, this bound, which holds for basic random points, was already better than Smoljak. And I can tell you this was a big surprise to the whole community. It was basically changed. A lot of IBC, a lot of people, especially from France, jumped on the train, and we were working on it very hard because this was a sign that we are on the right track. Yeah, so there must be something better than sparse grids. Sparse grids, these tensor product point sets kind of, they were designed precisely for this problem. And still, these random points here are just better. So there must be some better construction than that. And the question is, what is it? And I believe in the beauty of mathematics. If someone of you finds an explicit construction that solves this problem, you can get quite famous by that, I would guess. And the solution will be beautiful. My deep belief. Okay. Let's forget about that. Yeah, I'll manage. I still have some minutes. That's fine. So I wanted to show you a little bit more of the proof, but that's not possible for this high-end result. This result I just showed you is it really gets technical, infinite dimensional matrices and so on. That makes it's no fun, right? But it makes more fun if you restrict yourself to unweighted least squares and you allow yourself to prove an error bound where on the right-hand side you have the best approximation in L infinity. That's weaker, right? But we want to show that if the best approximation in L infinity is small, I can design a least squares method. Okay? I think many of you did that, by the way. That's what one of my questions was about that. If you assume a uniform approximation by B-spline series, I think that's really very much the setting I'm describing now. Okay. So we consider this an LP norm here, but we compare with best uniform approximation. And I changed the notation a bit, fits better to the thing. So we proved that unweighted least squares, so you fix some points at X, and you fix some space V, they are arbitrary, you don't need take your B-splines, then this method here can in general be a good method. And I will show you what it means. 3 words about the proof. That's very standard. I think most of you have worked with least squares, so I don't need to explain that too much to you, right? It is well known that suitable discretization results lead to nice properties of the least squares method. These discretization results are more or less something like the corresponding Gram matrix is well behaved, has good condition numbers, or some smallest singular value is this and that and so on, right? In my language, I talk about discretization, it is like this. Assume you have a set, P is between here, you have some set, some linear space of bounded functions, a finite dimensional subspace. If there is a constant and the point set such that the continuous LP norm can be upper bounded by a discrete L2 norm, then this implies that the error of least squares algorithms can be bounded by 1 plus this constant times the best approximation in L infinity. You can find that in many books. Also, yeah, the one of Shoemaker is probably well known to you. It's also in there. I checked it yesterday. So at the end of the day, what you probably only for L2, but whatever. So this means if you want to find a good least squares method, a good point set such that the unweighted least squares method has a good error bound, if you want to do that, then you need to solve this discretization problem here. Or not you need to, but if you solve the discretization problem, then you get something good for least squares. That's folklore, or you can find it in one of my papers. Yeah. Probably I said it earlier, so I take it back. This is my most beautiful result. But as I told you already, this result implies the other one, so they are very much related. So this has nothing to do with approximation, kind of, directly, only through the last lemma. So what we proved is, if you take an arbitrary probability space, an arbitrary subset of L2 intersected with you need the bounded function so that function valuations make sense, but you take an n-dimensional subspace, almost arbitrary, with dimension n, then you can always find 4 times n points, no matter how complicated your functions are. I don't care, right? You can always find 4 times n points such the LP norm can be bounded by this, say, discrete L2 norm here. So in particular, check p equal to infinity, you can always bound the supremum norm of a function by something like square root of n times the maximum of these values. And results of this type have an extremely long history, extremely important, sometimes called Marcinkiewicz-Zygmunt inequalities. That's why Marcinkiewicz and Zygmunt are involved here. Clearly, Kiefer and Wolfowitz are probably known to the statistics community. Optimal experimental design is really at the core of all of this. So we really needed to find an optimal experimental design in subsample format. Yeah, and clearly other names to know is Karl-Heinz Gröchenik, Glenn Bose, Andras Kroh, Volodya Temliakov. They were all working on that, on different aspects. And I think all but the dead people sent congratulations to this result. So it is a very general and powerful result, was applied already several times. Okay. So from this result, we just get what I just told you. For an arbitrary set, for an arbitrary n-dimensional subspace, there is a set of 4 endpoints such that the corresponding least squares method, unweighted least squares method, everything is explicit, every constant is explicit, that this can be upper bounded by the best approximation at L infinity times some factor here. And now let me give you some caution, because polynomials, as most of you work with, polynomials are a very special thing. And if you do something with polynomials, then even for infinity approximation, p equal infinity, you have a square root of n here, right? For polynomials, you only expect a log n. That's because for an infinity approximation, there's nothing else than the Lebesgue constant. And the Lebesgue constant for polynomials, if you make the points correctly, is only log n, which means, yes, you are right. For polynomials, you can do better. The same is not known for higher dimensions. The same is not known if you not take polynomials on the line, or it's not always. One has to be careful. One has to check the literature. But there is a better results for polynomials. This result holds for everything. Okay? So you cannot expect the same sharpness. And it's a very interesting question what the properties of polynomials are to improve that. I can name you one. I can already improve that by from square root of n to the 4th root of n easily by using the structure of algebraic polynomials. They form kind of an algebra, right? If you multiply two polynomials, they are still a polynomial of degree 2n. And so you can use this fact somehow to work around, but it goes into details. Okay, so again, in this result, you can use n log n suitable IID points. Suitable means you need to be able to sample from the density, and this depends on the precise space. There are examples where this is needed, as I already showed you. And the example, by the way, is not a complicated one. Let me just write down the complicated example. It's just the Sobolev space with p equal to 1. And this is kind of, yeah, I'm not sure if I need to write it. I can write it down. These guys here behave just like n to the minus s. That's known forever. While gn of w, that's also known forever. But here you at the end get some n to the minus s plus 1/2. Okay. So it is known that you can, for L infinity approximation clearly. So it's known to be sharp, and you only need an easy example like this, where you measure your derivatives in L1. Yeah, I should stop. So let me say there is even something more. We have some acceptance rejection rule to construct these points. And you get pictures like this. So really we can even design these points one by one on a computer. I could open my laptop and you can design your own optimal point set if you want to. So you really suggest a sampling point, apply an acceptance rejection rule, and so on and so forth. If it's accepted, rate is specified, blah, blah, blah. And so pictures look like this. So at the end, that's the normal isotropic smoothness that you know. Whenever I place a point, every point around it will be rejected because you don't want points to be too close. We heard that several times during this week. You want the points to be separated in a certain sense. So this is what you would expect. And a final point set is specified by its largest empty balls, right? The fill distance at the end gives you kind of the error, right? And this is what you basically can see here, because it shows you if I would be allowed to place 1 point more, I would place it in the biggest hole, right? Okay. That's the mixed smoothness case. And things start to get terrible. You see that for every point, I'm actually blocking a whole hyperbolic cross. And this whole thing here gets terribly complicated over time if you do it often. And it's almost impossible to see any structure at this point set. So at the moment, we do not know an explicit construction, a good one, but we have at least an algorithm that gives you a guaranteed point set if you want to, and if you can specify your basis. Yeah, this was on the torus, right? You see, go out in there. If you have some points with boundary, if you take just the square and you take here, I think that's the Chebyshev polynomial basis, then you see you would place more points close to the boundary, but you would make the weights comparably small, right? So already at the first point, you would not accept all of them. Yeah, some more pictures. Final remarks. So several results in LP. Other S numbers play a role. Geometry. Sometimes n random points are enough. I can't explain details. These are the open questions I would for the future kind of. So what is if the data comes from an unknown distribution? We do not really know yet. Are there settings where nonlinear sampling algorithms are much better? It's a very hard question, to be honest. Other classes of information, say radon measurements, X-ray measurements, or arbitrary convex functionals, we already have quite a lot in this respect, and many collaborators at the moment. So this is of quite some interest, especially X-ray and radon measurements, because our algorithm is quite fast. You can really build it into an MRI machine. No issues with that. And some of my more applied people tell me they are planning to do that. I would be happy to get the number of citations for it, but I do not want to be in an MRI. So, okay. Adaptive and randomized algorithms are a thing. And clearly, what are other good models for high-dimensional problems? And if you really want to know more about that, then I can say that I was allowed to write an Acta Numerica article. I was invited about a year ago. At the end, we ended up with almost 200 pages because the field really had quite some advance in the last, say, 20 years. And I was very happy to be allowed to summarize that. And we have extra chapters, so many things that I present here, just copy and paste from this article. I will, yeah. Thank you very much.